Hi there, this is Professor Bacon. I wanted to take this opportunity to perhaps go through a few problems with you from Chapter 1, 2, and 3, just so you have some ideas as to how I might approach some of these problems. I want to get a blank slide up here for my PowerPoint. Okay, so we can use that to work from. Alright, see if we can drag that over here. Okay. All right. In Chapter 1, I think the only item that I might notice that people have struggled with has been the question that asks about how much time it would take to double the number of cars produced for given a particular percentage increase. Let me pull that problem up here and get the exact numbers that I put down there. So it looked like problem number 7. So let's look here. Let's insert some text in here. Okay. We have 13 years during which time 6.7% increase per year was the rate of growth. Of automobiles in the U.S. Okay, so how do we approach that? Well, let's take a look here. Let me well, what if we start out and ask the question? Really what we're looking for is the equation that says if we start with 1, if we let n equals 1 be our starting number, because it doesn't really matter, does it? You could say 100, you could say 100,000, whatever it is. We want it to go from that starting unit at time t equals 0, and then to subsequently it becomes n equals 2 at some time t that we're looking for. Okay, and we'll designate x. X will be our interest rate, and 6.7% interest rate is 0.067, isn't it? Okay, so what does that mean? Okay, well, after 1 year, when t equals 1, so let's write that down, then the number will be the number you start with at the beginning of that year, which is 1, plus the interest rate, 0.067, won't it? Okay, or to write that generically, we just say 1 plus x. At t equals 2 years, then the number we'll get at the end of 2 years is the number we have at the start of that second year, right, after 1 year. So then n equals 1 plus x. That's what we started with the year, plus the percentage increase on that starting amount. So that means we're going to multiply x times 1 plus x. Okay, So the first part of this term, I don't know if you can see that, if I highlight to the first part, 1 plus x is what we started the second year with. And then at the end of the second year, that starting value 1 plus x was increased by the percentage x. Well, notice what you have there. You have 1 plus x, which you can factor out, which leaves you, again, 1 plus x. So this is actually, parentheses, 1 plus x raised to the second power. Where's my superscript? There it is. 2. 1 plus x squared. Okay. So at the end of 1 year, it's 1 plus x. End of 2 years is 1 plus x squared. Okay, so we keep going on and on. T equals, well, notice what's going on here. 1 plus x is the same as writing that as, let's write that up there, 1 parentheses, whoops, 1 plus x raised to the first power. All right, let's put a superscript on there, okay. Okay, so after year 1, the term 1 plus x is raised to the 1 power. After year 2, the term 1 plus x is raised to the 2 power. So after year whatever, let's say year 10, then the number would be parentheses 1 plus x raised to the 10th power, wouldn't it? And that would tell us how many vehicles were produced based on a 6.7, or that's our x value, that percentage increase in a 10-year cycle. Well, how many do we want? Right? How many do we want? Well, we want to go from 1 at time 0 to 2 at some time that we don't know what it is, right? So in essence, the n we're looking for, n will be, I still want capital N there, come on you, n will be 2, right? That's our ending value, a doubling of the original value. So we're going to substitute that n in our equation, parentheses 2 equals 1 plus, 2 equals, whoa, what happened to my thing there? 2 equals parentheses 1 plus x raised to the number of times it takes to go from 1 to 2 with a percentage increase of x. So the superscript here would be the unknown. This is the thing we're looking for. How many times do we have to cycle this process so that the 1 goes to 2? So I don't know what we want to call this. We'll just call it, we'll call it z. Okay, we're looking for z. What is the value of z that makes the equation 1 plus x equal to raised to the z equal to 2? Right. So we know what x is. Oops. Whoa! Don't do that. We don't want the superscript anymore, do we? Okay. So we know we've got equation 2 equals parentheses 1 plus 0.067. That was our x value, our percent increase, raised to the z power. Okay. Raised to the z power. Okay. Whoop. I can take off that superscript. Okay. Let's increase that a little bit up here. Okay. Make that a little darker. All right. So there we go. 2 equals 1 plus 0.067 raised to the z power. That superscript there is z. So I'm going to leave the rest to you on this one. That's the equation that will get you from unit of automobiles 1 to 2 in a certain time span. The z is the thing we're looking for. How many times do we have to repeat this to get to double from 1 to 2 at a 6.7% increase. Okay? All right, let's go on to chapter 2 in particular. Let me scroll down here in my text and find chapter 2. Sometimes the numbering in the book gets altered slightly as a result of additions and new things. So you might notice that while the assignment indicated pages 41 to 42 to 47, in the actual book you'll see that the problems start on page 41 with the particular problem that talks about the Leaning Tower of Pisa. The problem, the height of the Leaning Tower of Pisa is 54.6 meters, and how fast will lead weight dropped from the tower be moving when it strikes the ground, and how long does that take, right? So if you were to scroll back a couple of pages to the various formulas that are discussed in this chapter, you will note, and this should be on page 40, there's a list of formulas showing you how to find x given v0 and v and a and t and so forth. Okay. So I'll refer you to those formulas on page 40. You'll notice that the ones I just copied in here are not properly subscripted or superscripted. This part right here, AV, should be a subscript on V, and here's an A squared, that should be a superscript on T. So the format just didn't copy over the proper super and subscripts. Anyway, you know where the right formulas are and what they look like. I just want to give you some guidance here. Now, consider this particular problem. What do we know? Can we label? Looking at our formula sheet down here at the bottom, we have symbols for things. Remember, x is a distance, t is a time, v is a velocity, and a is acceleration. So if we consider this problem, this is a one-dimensional problem. The object is being dropped and it falls straight down. So we have a choice. Where do we put our origin of our coordinate system? It'd be like asking the question, if I have a ruler, okay, designating what are we going to designate as the origin, the starting point? Okay, in this case, you've got a vertical problem, so we have two choices here. We could designate the ground as a 0 point, or we could designate where the object starts and designate that as our 0 point. It won't make any difference in the time it takes, and it's only going to make a difference in the direction of the velocity. Well, here, let's start this way. I'm going to designate the ground. It just seems more logical to designate the ground as our starting point. So that means that our origin on the ground, so our starting value of the object is 54.6, isn't it? So let's call that x0 equals 54.6. Okay. So what is x final? What is x? X without a subscript, okay, in this first equation here, for instance, the value of x is referring to its position at the time t that we're interested in. And we're interested in where is it, at time t, it's going to hit the ground, obviously, so x will be on the ground, so that its final position, x, we can designate as 0. What else do we know? If we look at our formulas down here, for example, let me subscript that average term. Here in V average we have a V0 and a V. So V0 is our original and V is our final. Now final is just the instant it strikes the ground, so it's not 0 because it's resting on the ground. The final velocity is how fast is it going when it strikes the ground. Okay, V0 is how fast is it going when it starts to fall. Okay, well that means obviously V0 equals 0, right? And V final we don't really know. Actually we're looking for that, and right up here it says how fast is it moving when it strikes the ground. Oh, okay, that's cool. All right, so I might put that down as V equals question mark, just to indicate that it's something I'm looking for. What is the acceleration? Okay. Well, I don't really want capital A there, but that's what this program's thing's doing, isn't it? Okay. A equals. Well, because we have a one-dimensional problem here, and we've designated the ground as 0 and the top of the tower is 54.6, we've inherently said that the upward direction is positive, haven't we? Yeah. Okay, because we're going positive up. So acceleration of gravity being downward is directed in the opposite direction. So I'm going to give that a minus 9.8. Now I'm leaving out the units on this. You know, the proper units in meters and meters per second and meters per second squared. Okay. And do we know the time? Well, the answer is no, we don't know the time, but that's one of the things we're looking for t. Okay. All right, so now if you were to take these things that you know and place them into these equations, you'd have certain quantities that are unknown, in particular V and T, wouldn't you? Because you know what the X's are, you know what V0 is, and you know what A is. So to pick the right equation, we just look at what is it we're looking to solve for. We already determined that, didn't we? We found here that we want to solve for V and we want to solve for T, right? Okay. Well, let's pick an equation that has T in it, for instance. I'm going to highlight this one right down here. Down there, let's change that to, I don't know, green's not very good, is it? Let's change that to red. Highlight that equation, because if we plug in x and x0 into that, we've got 0 equals 54.6, v0 is 0, so that term drops out, and 1/2 a negative 9.8 t squared. Oh, that would allow us to leave, the only thing we don't know in there is t, and that's what we're solving for. So once we solve that equation, okay, once we solve that equation, then we've answered the question, what is the time? Then we can come back to, what about the one right before it, equation right before it? Since we found the time, we could then solve that one for the velocity at that time. Okay, so that's not too bad. Let's see what else. I'm kind of done with that problem. Let's take a look at the next problem in that is, man throws a baseball straight up at 25, how high will it rise? Aren't we doing exactly the same thing except we're moving in the opposite direction as we were in the previous problem? Yeah, so you're throwing it up so it's got a positive starting velocity instead of a 0 velocity, but it rises up, and at the point of its maximum height it has no speed, right? So if v0 is 25, then v at the high point is 0, because if it still had velocity it would still be rising, right? Sure. Okay, so we know what our two v's are in that problem. We know what our acceleration is. It's negative 9.8, and we're finding in this case the time and the distance, the value of x. Okay. All right. The problem on page 44, which is labeled problem 4, states the following. And I'll just insert it in here. Particle moves in a straight line. The position of the particle is given by the equation 5t, or what? 5t minus 20t squared. Okay. I'm going to come back here and grab one of this previous equation and bring it over to the next slide, because you will, I hope, begin to immediately see some connection here. Here, let's slide this down so it's kind of underneath the other one. Okay. All right. Okay. Well, anyway, all right. Demonstrations, compared. I'm just looking for something. I don't know why. Oh, here we are. Here's what I want. I want to show you that clearly in this problem, if there's a 5, the 5t is going to correspond to that term VOT, right? And the minus 20t squared is going to correspond to that term. So we could immediately do the following, and notice that there's no x0 term showing up in the actual equation, so we can immediately identify x0 is 0 and v0 is 5 and a is, well, what's a? Well, if minus 20 is 1/2 of a, then a is minus 40, right? So we've immediately identified by correspondence with this generic equation, the specific equation gives us this particular information here. Okay. All right. So when you come back to the problem in hand, is the particle accelerating? You can say, well, sure, there's a value of a, but it's negative, so we're slowing down. What is the value? You've got it, minus 40. What's the initial velocity? It's 5. Starting point is 0. Okay. Now the questions that really matter. What time does the particle return to its starting point? You might say, what does that mean? Well, think about it. This equation up here describes a particle which is moving with an initial velocity and an acceleration. But it's slowing down because it's got a negative acceleration, right? Okay, so it's moving with a positive velocity but a negative acceleration, so it's slowing down. So it's going to slow down and slow down. Finally, it's going to stop, and then it's going to start going the other way because the acceleration is still there. The acceleration is still in the negative direction. So the positive velocity gets reduced and reduced to down to 0, and then it turns around and goes the other way. Right? So at what time does the particle return to its starting point? Okay, so we know at t equals 0, the particle's at 0. So when is it again at x equals 0? Right? There's a solution to this equation, which you could find by factoring that equation, and the factor, you're factoring a quadratic equation. Factoring that equation will give you two solutions. One is t equals 0. The other one is the time it returns back to x equals 0. Okay? And then the second part, what is the maximum distance the particle had from the starting point? Well, you know that the maximum distance will occur when the velocity is 0. So maybe here, let's grab this equation from the previous slide, bring it over here, and paste it in. Okay. Right. Now, we know the acceleration is minus 40. We know that the x0 is 0. If we plug in v equals 0, we're saying that's the point x where the velocity is 0, given its initial velocity is 5 and its acceleration is minus 40. So we could solve that equation for the position x when the velocity is 0. All right. Grab a new slide, blank slide. Okay. I'm looking now at the problems on page 45 and 46. Just we'll point out a couple things, I guess. In problem 1, whoops there. In problem 1, please note that the units given on the acceleration are feet per second squared. So make sure you use acceleration of gravity in, well, if you use the 100 feet per second squared as the total acceleration in the first problem, then you can calculate the distance in feet from the kinematic formula. And then you can convert that distance to meters and miles. Okay? Now in problem 2, the acceleration of gravity is the only thing that remains, and that's negative 9.8 meters per second squared. Right? So you want to use the right units. Use the right units. So if you use acceleration in the second problem as negative 9.8 meters per second squared, then make sure the velocity of the rocket at that point where the fuel runs out is also expressed in meters, because you have what you have is a rocket has been accelerated up for 20 seconds, so it's going to have some velocity at this point. For problem 2, that it becomes the initial velocity of the second problem, which then as it rises, that velocity decreases, so finally at the peak it's 0. So since we're using negative 9.8 in that second problem, make sure that the initial velocity given the rocket at that starting point is in meters per second as well. For example, we know from the problem that in the first problem, for 20 seconds accelerating at 100 feet per second squared means that the rocket will be traveling at 2,000 feet per second at the point where the fuel runs out. Okay, well that's fine. 2,000 feet per second is fine. Okay, 2,000 feet per second. But we need to convert to meters per second in order to use the numbers 9.8 as our acceleration of gravity. Okay, let's see. Problem number 3. I don't know why that's so small. Let's go back to 32. Problem number 3. The concept in problem number 3 is really that there's regardless of the speeds of the two drivers, the total distance traveled by the two drivers has to add up to 278, right? So if x p, which is Paul's distance he travels, and x a is Aaron's distance he travels, then that has to add up to 278. Okay? And since each one is traveling at constant speed, the distance they travel can be related through x equals v times t, right? Okay. Okay. I think I'll leave that one at that. Oh, let's see. On problem number 5, how shall we say this here? Do I have a prop here? I think I got a prop here. Here's my ball. Okay. Now, if I launch the ball horizontally, the problem says a ball is thrown horizontally off a bridge at 25 meters per second. If I launch the ball horizontally, I have not given it any upward or downward speed. So the only thing acting on it in the downward direction is gravity. So you can think of it as like a problem, like a one-dimensional vertical problem. It's the same as dropping the ball from rest. If I don't give it any vertical speed up or down, then the ball will drop and take the same amount of time to fall down as it would if I launched it sideways. It's just that the sideways motion adds a horizontal distance to its landing point, but it doesn't change the time it takes to fall. You try that with a couple of, take a couple of pins and very carefully release one, drop straight down, and toss the other one sideways at the same time, and listen, and they'll both hit the ground at the same time, just that they won't land at the same place. Okay? So the horizontal speed in that problem, 25 meters per second, doesn't matter, does it? Because all we're really interested in is the ball's got to fall. It's going to fall 25 meters down. So it starts with no velocity. Acceleration of gravity is the only thing acting on it. And we can calculate the time of flight. Okay. Similarly, in number 6, let's just write that down here. You might think number 6, we're throwing it at 37 degrees, that's not really a one-dimensional problem. But just continue to read the problem and ask yourself, wait a minute, I know how far the building is away, and I know how much time it took to strike the building, and the only way it got from where it was launched to the building was to have a horizontal speed Well, I'll let you kind of finish that thought. Don't overthink these problems. Sometimes there's going to be data in the problem that you might think you have to use all the numbers in every problem. You don't. You think about what you need, and what's important, and what's not important. Okay, as part of evaluating critical thinking type process. Okay. Let's see here. Just sort of glancing at some more of these problems. Number 10, the only thing about number 10 that might give you some pause is that it's a high velocity. 400 meters per second is a high velocity, so that means that you're going to get a large acceleration as an answer, because this bullet traveling at 400 meters per second is going to stop in a distance. Where's my centimeters? Are there? In a distance of about that. Yeah, that far. About that far. Okay. A little under half an inch. So the ball is going to come to a stop very quickly. Short distance, high velocity. Okay, so that means it's got to be a very high acceleration or deceleration, a negative acceleration. So we get a big number for it. Answer to 10A. And then from the acceleration you get in 10A, you can figure out, okay, how much time. It had a high velocity, it stopped in a short distance, you're going to find it stopped in a very short amount of time. Okay. All right, let's take a look at Chapter 3. Chapter 3. On page 55 in Chapter 3, let's grab ourselves a new slide here. Yeah. Chapter 3, page 55. Okay, are the equations that are summarized in the x and y direction, and then in particular those are general, and we want to make them very specific to the case where we only have acceleration in the negative y direction. In this case 9.8, the acceleration here on Earth. So those equations then simplify down to the set given at the bottom of page 55, which I'll copy in right here. And maybe clean up a little bit because it doesn't take the subscript and superscript like I wish it would when I do that copy to PowerPoint. We'll see what we can do here quickly to clean these up a little bit. Okay, these equations describe the motion of an object undergoing two-dimensional kinematic motion under the influence of an acceleration in only the vertical direction. Okay? Only vertical acceleration. And in this case, the vertical acceleration is a 9.8 in the negative y direction. Since we have two directions to consider, that's why we have in particular subscripted the velocity and position with x and y symbols. I think I got them all there. There's one more. Sorry, one more. So when it says VOX, that would indicate the initial velocity in the horizontal direction. Okay. If it says VOY or VY, okay, that's obviously velocity in the y direction, either VO being original or VY being the velocity at some later time. Okay, notice in the top equation here it tells us the distance x it travels is the starting velocity in the horizontal direction, VOX, times the time t. And VOX at all time is, Vx at all time is the original horizontal velocity. So the fact is, we're throwing an object at some angle, okay, but the only acceleration occurring is downward, so the horizontal part of that velocity doesn't change, but the vertical part of that velocity does change as a result of the acceleration of gravity. VOY and VOX are the components of the velocity described. Just want to scroll back here a little bit. Where would be a on page, well, here, let's just copy this. Page 52, there was a problem example given which showed VOY and VOX. Okay. And of course, I'm trying to put a symbol in here that is the theta for the angle, and the program doesn't like that. Let's see if we can change that font to theta. There we go. Okay. So, I need one more. I need one more. Oh, there. VOX and VOY. Okay. Okay. So these two equations here define for us what VOX and VOY are. Those are the initial horizontal and vertical velocities given the angle theta and the initial launch velocity v0. Well, let's grab a problem that we could use here. Okay. Well, let's just take a look at number one. Put number one right up here, okay? So what do we know in number one? Well, we've been given V0 is 18 meters per second, and the angle is 41 degrees. Alright, now, because we have the angle, we can take that and bring it down here and put it in our formula. Right? There and here. Okay. And we've got our V0. Same thing. We can take that and bring it down here and put it in there and put it in here. Okay. So we have our, that means, because we know V0 and theta, that means we know VOX and VOY. Right? So given that, okay, let's see what we can do. Given that VOX, we can then come back up here and we can put that in here. And VOY, well, that'll go in to our formula. Well, a bunch of places, won't it? Right? Okay, so we can put that VOY, say, into this one here, or that one, or even the bottom one. Okay? So lots of different choices. Just have to ask the question, well, what did we want to know? Well, we want to know the time it takes to reach its highest point. So what do we know about the highest point? Okay. Vy equals 0 at the highest point. Right? Vy equals 0. Okay. Okay. So, Vy equals 0. Well, here's an equation, the bottom one there on our list. Okay. We'll bold and underline that equation and make it all colorful. Okay. That equation, we could say 0 is Vy, and we know Voy because we calculated it right here. We put that in, and 2 times 9.8, that's negative 9.8. It's already in there because this is a downward acceleration. We could solve for y. Oh, wait a minute. Well, we weren't trying to solve for y. Well, that's all right. If we could solve for y, and maybe the question would be, how high did it go? Well, once we know how high it goes, we could then put that back into the previous equation right there. Okay, and solve for t. I like that color better, right? Because VOY is the known quantity, and 1/2 of 9.8 is 4.9. We have ourselves another little equation there where we know the y, and we've got the two terms, and well, it's quadratic, but that's all right. We know how to solve the quadratic equation from the quadratic formula. So that would be a pathway you could follow. Okay. All right, let me just glance through here. Sometimes people have questions on number 8. Number 8. Okay. Number 8. Because the thing about number 8 is this. Let's take a look at what we have. A ball is thrown at an angle, right? So we've got 37 degrees. And we've got a distance of 55 meters and a height of 3.84 meters. Okay. Change that to a symbol. Okay. Now, inherent in this problem is the assumption of where we're starting, right? It doesn't say where we're starting, but what do we assume? Well, we have to assume we're starting at x0 equals y0 equals 0. Okay? So we know the location of the starting and ending points. We know the angle And of course we know the acceleration is negative 9.8. We still have our list of equations from before. Matter of fact, I'm gonna grab that one, place that over here, and I'm gonna grab the first one there and bring that over here. Okay. Alright. Those are two equations that I want to think about because, okay? Oh, and sometimes we don't include the starting point because it's generally assumed to be 0, but to be more explicit, let's actually put the starting point in both of our equations, y and x, so that it's clear that if the starting point isn't 0, then we would have a place to put it. Okay. So notice in this equation, the y equation, it says y is where it ends up. So that's 3.84. y0 is where it started at 0. VOY, we don't know all of that, but we have a way of calculating VOY and VOX. Remember our formula back here? VOY and VOX are given by the sine and cosine components of the initial velocity V0. And that's what we're looking for, the initial velocity. We do know the angle is 37. Okay, so if we go ahead and take that formula and bring it over here, paste it in, okay, put in our theta, okay, put in our theta, so take that 37 there and bring it down and put it in our formula here and here. So then you can have an expression that says V0 sine 37, V0 cosine 37. All right? Sine and cosine of 37, sine of 37 is 0.6 and cosine is 0.8. So we're going to have V0 times 0.8 and V0 times 0.6 for our OX and OY pieces. Then plug those into the previous two equations with the values of x and y given, and you're going to end up with two equations that have two unknowns. Right? You're going to end up with two equations involving t and v0. So solve by substitution. Solve by substitution. Okay. All right. Hope that helps. See you in the chat room on Tuesday night, and email me with any questions that you might have. Thanks.